The manufacturing process begins with cutting raw steel material into precise lengths using CNC, computer numerical control machines. CNC technology ensures high precision and consistency. The raw steel strips are loaded into the CNC machine, where automated blades or laser cutters slice the material into exact lengths as specified in the design. Simultaneously, holes are punched into the steel strips. These holes are necessary for mounting purposes and aligning the leaf springs during assembly. CNC-controlled hole punching guarantees uniform spacing and alignment, which reduces errors during subsequent steps. High-speed punching presses or hydraulic systems are often used for this process, enabling efficient production without compromising quality. Spring straightening. Drilling holes. Additional holes are punched into the leaf spring using hydraulic or mechanical presses. These holes may accommodate bolts, fasteners, or additional mounting components. The leaf edges are tapered to reduce thickness and improve flexibility. Tapering is performed using grinding or milling machines, which carefully remove material to create a smooth, gradual reduction in thickness. This process is critical for distributing stress evenly along the length of the spring, enhancing its ability to flex under load without cracking. Proper tapering also improves ride comfort by allowing the spring to compress and rebound more efficiently, making it well suited for heavy-duty applications. The ends of the spring are cut, punched, pressed, or formed into the desired shape to facilitate installation. This process often involves forming loops or specific angles. Automated conveying systems transport the partially processed springs between workstations. This reduces manual handling, increases efficiency, and minimizes errors. Precise end cutting further refines the spring's shape. The ends of the springs are rolled into specific shapes to form eyelets or other attachment points. End rolling is performed using specialized rolling machines that bend the ends of the spring into circular or oval shapes, depending on the design requirements. The process uses high-pressure rollers to gradually shape the steel without creating cracks or weaknesses. These eyelets or loops provide attachment points for bolts or shackles, which secure the leaf spring to the vehicle chassis. Properly rolled ends enhance the durability and load-bearing capacity of the spring, ensuring long-term performance in suspension systems. Heat treatment begins with quenching, where the springs are heated to high temperatures and rapidly cooled in oil or water. This hardens the material and improves tensile strength. Air linkers are formed to maintain accurate alignment and spacing. This step enhances assembly precision and ensures proper function under load. Robotic systems automate the bending, shaping, and assembly processes. Advanced robotic arms equipped with sensors and programming can accurately bend and form the steel into complex shapes required for leaf springs. These systems handle repetitive tasks with precision, reducing errors and ensuring consistent quality. Robotic automation also speeds up production and allows manufacturers to scale operations while maintaining high standards. Tempering follows quenching to reduce brittleness. This process involves blasting small steel beads onto the surface of the springs. Shot peening improves fatigue strength and resistance to cracking by inducing compressive stress. Individual leaves are assembled into a stack to form the complete leaf spring. Clamps, center bolts, and rebound clips secure the assembly, ensuring stability. Pre-pressing applies initial stress to the springs, simulating the load they will experience in use. This step eliminates weak points and ensures proper alignment. Springs undergo fatigue testing to evaluate their durability under repetitive load cycles. Rigidity testing measures the stiffness and load-bearing capacity of the springs. The springs are coated with protective paint to prevent rust and corrosion. This step improves durability and extends the lifespan of the product. Identification marks, including batch numbers, specifications. Finally, hardness testing is performed to verify the material properties and confirm that the springs meet required standards for strength and resilience. The production of metal springs involves precision engineering to ensure strength, durability, and performance. The process begins with selecting steel wire, which is either supplied as rods or coils. Two primary methods are used to shape the wire into springs: coiling and winding. Coiling is suitable for wires with diameters up to 26 millimeters, often pre-tempered for strength. This process uses CNC-controlled machines to create precise spring designs. Specialists monitor the process carefully, as variations in material properties can affect the final product. The spring rate, which determines the force required for compression, depends on material type, wire diameter, coil spacing, and the number of turns. Winding, on the other hand, is used for thicker wires up to 55 millimeters. The wire is wound around a mandrel, and in most cases, tempering is done after forming. While this method is slower, it allows the processing of larger diameters, including wires up to 32 millimeters, using cold or hot forming techniques. Post-processing steps are critical for enhancing spring quality. These include grinding, deburring, and chamfering to smooth edges, followed by stress relief treatments for durability. Shot peening further strengthens the springs by blasting them with steel pellets to create a uniform, hardened surface. A final step called setting compresses the springs fully to prevent future loss of strength. Springs are then tested to ensure they meet all design and performance requirements before mass production begins. To protect against corrosion, the springs are coated with epoxy or polyester resin, making them ready for long-term use in demanding environments. This comprehensive manufacturing process guarantees high-quality springs for a variety of industrial applications. The WIM-100-H CNC Custom-made hot spring coiling lathe coiler by Fortuna Fettern is an advanced machine designed for precision manufacturing of large compression suspension springs. Engineered to handle wire diameters of up to 100 millimeters, this CNC-controlled lathe coiler is ideal for producing high-performance springs from tapered bars or bars with cylindrical straight-cut ends, meeting specific customer requirements. Built with cutting-edge automation technology, the WIM-100-H ensures exceptional accuracy, repeatability, and efficiency. It is suitable for both automatic and semi-automatic operations, allowing flexibility for diverse production demands. The CNC control system provides seamless programming, enabling operators to achieve complex spring geometries and tight tolerances effortlessly. Designed for hot coiling applications, the machine delivers robust performance under high temperatures, making it perfect for heavy-duty spring production tasks. Its sturdy construction ensures durability, while advanced safety features protect operators during high-heat operations. Fortuna Fettern's custom solutions guarantee that the WIM-100-H can be tailored to match unique specifications, supporting industries that require precision-engineered springs for demanding applications. Helko axe heads are individually forged by hand using a drop hammer on open dies, a traditional method that emphasizes craftsmanship and durability. Skilled blacksmiths employ a drop forge, utilizing tongs to manipulate and shape heated steel as a hammer repeatedly impacts it. Once the desired shape is achieved, the Helko Work crown logo is stamped into the cheek of the axe head. Minimal finishing work is performed afterward to preserve the natural forging marks, making each axe head a unique piece of functional art. The quality of an axe depends significantly on its hardness and temper. Helko axe heads are tempered to strike the perfect balance between toughness and edge retention. If the steel is too soft, it dulls quickly, necessitating frequent sharpening. Conversely, excessively hardened steel risks chipping or cracking under stress. Helko's mastersmiths have honed their techniques over generations, ensuring their axes feature an optimal Rockwell hardness for durability, sharpness, and ease of maintenance. Helko handles are crafted from sustainably sourced grade A American hickory, renowned for its strength, flexibility, and shock absorption. Logs are milled into planks and air-dried for 9 to 10 months to achieve ideal moisture content. This meticulous drying process ensures durability and performance. Hickory's straight grain, coarse texture, and receptivity to finishes make it an excellent material for axe handles. Variations in color, from pale yellow sapwood to reddish-brown heartwood, highlight the wood's natural beauty without compromising strength. To complement the craftsmanship of the axes, Helko's sheaths are made from vegetable-tanned, full-grain cowhide leather. Each sheath features a heavy-duty welt for added blade protection. The mill is capable of producing wire rods ranging from 5.5 millimeters to 16 millimeters in diameter. Additionally, it manufactures straight bars and rectangular cross-sections, RCS, ranging from 12 millimeters to 140 millimeters. The process begins with the roughing mill, which features two 710 millimeter stands. An automated manipulator and trough system is used for bar feeding. This ensures precise handling and positioning of the bars, optimizing the efficiency of the process. In this step, the bar is turned at a 45-degree angle and fed diagonally into the mill. This orientation facilitates the rolling of equal-sized squares, ensuring uniformity and structural integrity. The intermediate mill consists of 6 housingless stands arranged in an HV, horizontal-vertical configuration. This setup allows for controlled deformation and precise shaping of the bars. The crop and cobble shear is employed to crop the ends of the bars and remove any defects or irregularities. It ensures uniform length and enhances product quality. The finishing mill features 6 additional housingless stands with an HV configuration. Equipped with vertical loopers, it enables fine adjustments and accurate finishing of the bars to meet size specifications. This shear is used for high-speed cutting and sectioning of the rolled bars. After rolling, the bars are transferred to a turnover-type cooling bed. The final stage includes a run-in roller table, equipped with a braking slide and an automatic rake-type cooling bed. Steel rebars, or reinforcement bars, play a crucial role in construction by providing structural strength and stability to concrete structures. The process begins with directly reduced iron ore as the primary raw material. It is charged into 30 metric ton induction furnaces using giant electromagnets. The raw material is melted at a temperature of 1,650 degrees Celsius within a cordless induction furnace, which consists of a refractory container surrounded by a helical coil connected to an alternating current source. This method ensures efficient melting and minimal energy loss. Once melting is complete, the molten metal is extracted from the furnace into a casting ladle. Nitrogen is purged through the molten metal to ensure homogeneous chemistry and uniform temperature throughout the ladle. This process is critical for maintaining consistent quality during subsequent processing. The solidified billets are cut to size by online billet shears and then transferred to the rolling mill without delay, preserving heat and minimizing energy usage. The rolling process begins in the roughing mill, followed by further size reduction in the intermediate and finishing mills. PFI employs advanced rolling and guiding technology sourced from Daniele Magazzum, Italy. A loop scanner monitors the bar flow, ensuring a perfectly tensionless rolling process. This precision guarantees uniformity and the desired round shape of the rebars. The rebars undergo a quenching process that establishes their tensile strength. They can be tempered to meet different strength requirements, ranging from Fe 415 to Fe 600, based on customer demands. The bars are then cut into standard 60-meter lengths using online dividing shears. In the cooling section, atmospheric tempering is carried out at the cooling bed. The hot core releases heat to the surface, resulting in a soft core for flexibility and a hardened outer surface for strength and grip. This process also makes the rebars corrosion and stress resistant. After cooling, the rebars are bundled automatically using PLC-controlled machines from Sundbersta, Sweden. Both straight and bent bundles are prepared based on customer specifications without manual intervention. Quality control is an integral part of PFI's production process. Stringent tests are conducted after rolling to verify the quality, strength, and safety of the final product. The rolls used in the process undergo 100% machining and embossing in the in-house workshop to maintain high standards. The finished rebars are stored in an 80,000 square feet indoor warehouse, categorized by size, grade, and lot numbers. This organized storage system facilitates efficient inventory management and timely delivery. The rebars are then shipped through various retail channels to meet domestic and international demand. The manufacturing process takes place in an area of 15,000 square meters, equivalent to approximately 2 football fields. The facility has a storage capacity for 2,500 slabs, ensuring a steady supply of raw materials for uninterrupted production. The slabs are fed into one of the 4 heating furnaces, where they are heated to a temperature of 1,250 degrees Celsius. This high temperature softens the steel, making it malleable for further processing. The energy required to heat the slabs is significant, consuming an amount equivalent to the annual energy needs of 200,000 households. Once heated, the slabs are transferred to the rough rolling mill. Here, they undergo an initial reduction in thickness and width, using presses capable of exerting up to 2,200 tons of force. The width of the slabs can be reduced by up to 300 millimeters during this stage, preparing them for further refinement. The semi-finished slabs move to the finishing mill, where they are further rolled to achieve the desired thickness. The rolling process uses powerful motors with a combined drive power of 2 by 20 megawatts and a rolling force of 5,500 tons. Thickness is reduced from 250 millimeters to as low as 45 millimeters in this phase. The finishing mill consists of several rolling stands arranged in series, each equipped with high-precision rollers. These rollers progressively reduce the thickness of the slabs in multiple passes, ensuring uniformity and consistency. The process involves maintaining precise control over temperature and pressure to prevent defects and enhance the mechanical properties of the steel. Sensors and automated systems monitor the rolling process in real time, adjusting parameters to meet exact specifications. The powerful motors provide the required torque, enabling smooth and continuous rolling operations. In the final rolling stages, high-powered stands with a drive capacity of 30 megawatts, about 40,000 horsepower per stand, further refine the thickness and width of the steel strips. The final product can have a thickness ranging from 25 millimeters down to 1.5 millimeters and a width of up to 2,020 millimeters. The cooling system has a capacity of 100 million cubic meters per year, equivalent to the water consumption of 80,000 households. The temperature of the strips is reduced from 750 degrees Celsius to 50 degrees Celsius, ensuring they are ready for coiling. The cooled strips are wound into coils with diameters of up to 2,100 millimeters and weights reaching 35 tons. The length of each strip can extend up to 1.5 kilometers, making the coils ideal for transport and further processing.